This is a short summary video of our recent paper on the mid-infrared galaxy luminosity functions from the entire AKARI NEP deep field. My collaborators are listed here. One of the biggest questions in astronomy is in the long history of the universe, when and where stars were born. This is called the cosmic star formation history, and we want to reveal it. Many efforts have been done from using the ground-based telescope to reveal this cosmic star formation history. However, ground-based telescope can only observe UV and an optical light of the distant galaxies. But because this UV and optical light are obscured by dust, therefore those measurements can only give you the lower limit of the cosmic star formation rate density. In one estimate, at redshift 1, 80% of the star formation is obscured by dust. So how do we reveal this, how do we measure this obscured star formation? Our answer to this question is AKARI Space Infrared Telescope. Infrared light can observe the light obscured and re-emitted by the dust. Therefore, infrared light can capture the obscured part of the star formation. However, most of the infrared light doesn't reach Earth. Therefore, we need a space telescope to observe in infrared. Therefore, we built and then launched AKARI Space Infrared Telescope. This is a video at the time of the launch. And now AKARI is in space, so we can make the infrared observation. One of the nice features of the AKARI is its continuous 9-band mid-infrared filters. This is the AKARI's filters in mid-infrared. From 2 to 24 micron, AKARI's 9 filters continuously covers the entire mid-infrared range. It had a large gap between ILAC 8 micron and MIPS 24 micron. Here is a large gap. So if you are interested, the feature of your galaxy falls into this gap, then you have a problem. So in this AKARI's 9 mid-infrared bands, we did a deep survey in the NEP field. So this is AKARI data. It's wide area of 0.67 square degrees in 9 mid-infrared filters. And especially this 7 micron to 18 micron data, these are Spitzer does not have these filters. I want to emphasize this continuous 9-band deep mid-infrared imaging is very unique. It doesn't exist anywhere else. So AKARI NEP deep field is a treasure AKARI left for us. And using this AKARI's mid-infrared data, we estimated the cosmic star formation rate history in our previous work. Here's our previous result. Cosmic star formation rate density is increasing towards the past. However, our previous work had a big problem. Not all AKARI NEP data were used. Because we had optical near-infrared coverage in much smaller 40% of the area. We were only able to use that area for our previous work. And this optical near-infrared coverage is needed to calculate accurate photometric redshift, which is needed to compute infrared luminosity of individual galaxies. I'll show you in this figure. This is the entire AKARI NEP deep field, and this is AKARI's data. However, we only had the optical near-infrared imaging in this 0.25 square degrees, which is for 40% of the area. So in our previous work, we were only able to use this area of this area. As a result, our previous luminosity function suffered from poor statistics. As you see, those data points are jumping up and down because of the poor statistics. To fix the situation, we took the new and larger data using Canada, France, Hawaii for middle telescope. Here. And then this new data covers the entire AKARI NEP field. So our previous area was here, but this new data covers the entire field. Therefore, our sample is now a factor of 2 larger than previous work. And then we obtained accurate photometric redshift based on this CFHT megacom and VOCom data. I showed the result from 8 micron luminosity function. 8 micron is an important wavelength because it is dominated by strong PAH emission, which is an indicator of a star formation activity. What's nice about this AKARI's 9-band mid-infrared imaging is no matter what redshift your 8 micron feature is, because the filters are continuous, one of the filters can capture the 8 micron emission directly. For example, if your galaxies are redshift 0.4, 11 micron filter can capture the rest frame 8 micron emission directly. If your galaxy is at 0.7, redshift 0.7, 15 micron filter can observe rest frame 8 micron. The same thing with redshift 12.25, 18 micron filter can observe 8 micron emission. And 8 micron emission goes into 24 micron filter at redshift 2. In a previous work with, for example, Spitzer telescope, because there was a gap between filters, so if your 8 micron emission is in this gap between filters, you needed to use SED model to extrapolate to estimate 8 micron luminosity. However, this extrapolation from SED model was the largest uncertainty in previous work. But using AKARI, we don't have this uncertainty. Resulting 8 micron field luminosity function is shown here. And as you see from redshift 0.4, 0.8, redshift 1, redshift 2, there's a steady and strong evolution of mid-infrared luminosity function. And then as you see, our luminosity function is much smoother, stable than our previous work because of the factor 2 larger sample. And I show you one more result on total infrared luminosity function. To estimate the total infrared luminosity function, we, even with 9 bands, we still need to do the SED fit. But however, so this is an example of an SED fit, and you see AKARI's data points, 9 data points here, and then you fit SED models. However, in case of Spitzer, you only have 4 data points around here. So even we have to do SED fit, 9 medium-infrared bands still help to do good SED fit. Now jump onto the result. This is based on Bmax and a complete race connection. As you see again, rate is 0.3, 0.5, 0.8, and 1.5. Again, you see steady and a strong evolution. Again, luminosity function is smoother because of the larger sample and smaller errors. What about the cosmic star formation history that we want to reveal? Once we have infrared luminosity function, if we multiply infrared luminosity and integrate, then we get infrared luminosity density. And this infrared luminosity density is directly related to the star formation rate density in this equation. So we can estimate the cosmic star formation history. And then here's the result. Our cosmic star formation rate history looks like this. And then by the time of redshift 1.5, cosmic star formation history was more than factor of 10 larger. And our results are in good agreement with this previous work, but I should emphasize here that our measurement was done more accurately because of the AKARI's 9mm infrared bands. And I said this is all revealed by AKARI. By that I mean this lowest redshift data points was from our previous work based on the AKARI all-sky survey. So this cosmic star formation history was entirely based on the AKARI data. I wrap up here. AKARI's 9-band continuous linear infrared exists nowhere else. And we obtained the new CFHT imaging data. This covers whole AKARI NEP deep field, and then as a result, our sample size increased by a factor of 2. And updated infrared luminosity functions and infrared star formation history are more accurate and more robust against cosmic variants. Please see more details in our paper. Thank you for listening.